Well, I'd like to welcome you all here today. It's a very special day. We have a big event this afternoon with Professor Galambos, and also in conjunction with this great thing that's happening this afternoon, it really gives me great pleasure to introduce a former colleague at the University of Minnesota, Professor Roberto Leon. He has had a history since he's been here. He was a faculty member at Georgia Tech. He's now a faculty member at Virginia Tech. And his title, as you can see on the screen, is a Burroughs Professor of Construction Engineering. He has a long and storied career, received numerous awards, was president of ASCE SEI, the Structural Engineering Institute. He has served on the AISC Specification Committee. He has research in reinforced concrete, steel, composite construction, and also in masonry structures. And without further ado, it gives me great pleasure to introduce Roberto Leon. Thanks, Roberto.
Thank you very much, Kathy. It's a great pleasure to be here. I was telling somebody that the last time I lectured in this room, it was my pre-tenure lecture to the entire faculty. And I remember distinctly, it gives you an idea of the technology at the time, Professor Galambos tried to dissuade me from using a dual carousel projectors. Anyway, so I'm going to talk a little bit about what a topic of my interest is not really research in that sense, but a topic that I find very apropos. And before I start, I must put this disclaimer up there because everything that you're going to hear are basically my opinions, and everything that I'm using is in the public domain. But all the things I'm going to say are my responsibility. So just to give you, for those of you who don't know me, I was a beautiful baby. And I've had the opportunity of moving around a lot and living in different places, and I think that's been terrific. Sort of a recent shot of my family, my son and my daughter and my wife, and my son is married, and I have a beautiful daughter-in-law and a great granddaughter, and hopefully I'll be a grandfather again for a second time very soon. So things are changing for me. Over my career, as Kathy says, I've done a lot of things, but the last thing that I kind of got pretty interested in is in forensic engineering. And that's when I went to Virginia Tech, and one of my ideas was to start a course on that at Virginia Tech. And the origins of that are actually here in Minneapolis. My first sort of foray into forensic engineering was with the collapse of the formwork for the arch bridge that was replacing the old one in Hennepin Avenue. And this was a pretty interesting situation because it was a failure of formwork, and I actually didn't participate in the investigation per se. If you're interested, there is a PCA report that's now online about the whole investigation. I serve as the expert for the Board of Licensing for engineers here to determine whether the license of the engineers for that part of the project should have been taken away. And the whole thing hinged on web crippling. And my job was to determine or to tell the board whether web crippling was something that got taught and was important enough that the engineers should have known about it. And I was a young, stupid assistant professor, and I said yes. And they actually took away the licenses for the engineers as a result of that. I think my experience today, I would have handled that a little bit differently. But I've had lots of other experiences. I was not, for example, involved directly on the I-35W bridge, but I was very involved with a colleague at Georgia Tech, Don White, in looking at both the analysis and the testing of full-scale truss connections. And this is not a half-scale, I should say, not a half-scale version of the one that collapsed. It's as close as you can get. I've also had the opportunity of doing a lot of research on seismic design and post-earthquake investigations. I happened to be in Christchurch, New Zealand, when the earthquake occurred back in 2011, and I was there for 3 months afterwards. So I saw, how in the longer term, how a city reacts to a disaster like that. I had been to other situations like that, but you usually go for a week or 10 days and then you disappear, and you kind of lose track of what's happening. So that was quite interesting because in this particular case, there were probably, I believe, around 160 casualties in this earthquake, and about 100 of them occur in 2 buildings, what we call a killer building, and this is a terminology that's being used now in Southern California for certain types of buildings that don't have much redundancy or have certain pathologies that make them very susceptible to failures. I've also done some consulting looking at things like how well constructed things are, and so this is the knuckle or the edge of an arch, and I'm not, does this have a pointer? There's this point here, right there. I'm short, but I can reach. And the issue was whether this has all kinds of plates and welds and so on, and it was a question of whether the distortions that existed were meaningful enough, or if the piece as fabricated was fit for purpose. So I've done things like that, and then I also do things on my own, such as looking at buildings like this that you wonder who decided in a high seismic zone to do this kind of thing. This is in Europe, by the way, Jim, so that we wouldn't allow this in the US, hopefully, but you just wonder why people do that, and so there are failures, right? And there are small failures, right? This is before lunch, so don't look at that. And there are big failures like that, right? In general, we just define failures as the failure to provide intended performance. But if you look at the literature, there are lots of people, and many of you are probably familiar with Henry Petrosky, who look at, says it behooves us to beware of the lure of success and listen to the lessons of failure. So that's what I've been trying to do. And successes and failures are just part of our everyday life, right? At almost every level, right? And so I think it's interesting to investigate that. And some fairly famous philosophers have looked at this, and I don't know how many of you are familiar with Immanuel Kant. And this is proposition 6 out of, this is the question, there will be a quiz at the end. How many propositions are there, and which is number 9? Okay. But out of the crooked timber of humanity, no straight thing was ever made. And the idea here is that we really, we're going to have errors. We're going to have to learn from them. All right? And so that's where we are at. And over the last few years, I've taken sort of a more sociological approach to this. And so there are a couple of people out there. I'll mention the first one is Catherine Tierney, and she used to be a professor at the University of Colorado. And her hypothesis is that risks and disasters are produced by the social order itself, by governing bodies, organizations, groups that push for economic growth, oppose risk-reducing regulation, and escape responsibility for tremendous losses when they occur. This is very different from what an engineer would think about. And so this is where I'm going with it. I strongly, if you have not read, her latest book is entitled Disasters, and it's a very easy read. If you have not looked at that, it'll be a nice book to read for you. Not really summer reading, but maybe winter reading. But the issue is really that we are beginning to see sort of a different type of failure, what is called nowadays in the literature sometimes a NATEC failure. And this is the confluence of a natural disaster and human intervention. And so Fukushima in Japan is an example of that, right? These are very low probability, but very high impact type situations, right? And basically they're triggered by some event, but the human intervention makes them worse as we go along rather than better. And if you're interested in seeing or listening to a good example of that, out there in Coursera, there is a lecture from a professor of nuclear engineering at MIT that talks about the aftermath of Chernobyl. And you don't have to be a nuclear engineer to understand what he's saying. And he just goes step by step of how many human interventions led to the disaster that was Chernobyl, and how many times sort of the right human intervention could have, at least in that case, reduce the consequences. And so these kinds of events are what we call cascading events, right? And so one thing leads to another, and somehow things just snowball. So this is a particular interest of mine. And you can find it almost everywhere. And so yesterday in the morning, I was just reading my email, and one of the things I get is the thing from the equivalent of ASC in Britain. And so they are talking about their infrastructure and cascading risks from climate change. And again, I teach a class on failures, and I basically have a failure of the day picture. This is the one from yesterday. This was a bridge under construction in Missouri that came down. And if you look at that bridge, right, it doesn't look like an unusual bridge at all. These things should not be happening, but they keep happening. And construction is by far the most dangerous of our industries. So with that as sort of a background, I'm going to talk about two events. One is the Metro City Linea 12, and then the Pittsburgh Fern Hollow Bridge. I'm not sure if I'm going to get to very much of the second one because the stories are long. But my interest is in discussing and contrasting these two very different failures. One is what you would call a very large project. There were major casualties. One is brand new, one is old, one is in the US versus a developing nation. And there are lots of things like that that you can contrast, but there are lots of parallels, I think, because the issues are really whether there is engineering malpractice, what I would call engineering malpractice versus human error. Human error is something that we will accept. Engineering malpractice is not something that I would. And then more interesting, and I'll try to weave this into the story, are sort of the political forces that drive some of these issues. And then getting back to another of the sociologists, Charles Perrow, who's a professor, or used to be a professor at Yale, who basically says that it's not that we are having more disasters nowadays, but because we have concentrated people, resources, and manufacturing in all kinds of things in certain locations, the consequences are far larger than they used to be. And then whether we as the public are involved at all in some of these issues. So let me start with the Mexico City case. I owe a lot of the data here. We collaborated, a former student of mine, Tiziano Perea, who's a professor at the Universidad Autónoma Metropolitana in Mexico City. And so Mexico City, as you most probably know, is a huge city. Is the second largest city in Latin America and one of the largest in the world. It's sitting in a very particular geological setting. Here is a diagram that shows the growth of Mexico City. And I just want to point out the difference between the yellow area, which is Mexico City in 1960, versus Mexico City in gray today. Okay, an enormous explosive growth. In order to accommodate that, there has been a lot of construction of public transportation, but there was a little area down here at the corner where there was no metro. And there were lots of studies about this, and in the early 2000s, the Mexico City government decided that they wanted to build a metro there. But in the previous image, I should have pointed out that most of the area shown there is an old lake bed. And so Mexico City sits on very soft soils. So this is in case there was somebody from the geotechnical side, I had to show something about soils. So these are the periods of the soils in Mexico City, and the line that you see, that black line, is where this metro line was going. So this was a very challenging situation because, again, Mexico City sits on a very soft basin, and there are very large earthquakes in the off the coast, right? This is sort of the continuation of the San Andreas Fault. Here's the so-called Guerrero Gap, which is where we're expecting a very large earthquake, because you can see lots of earthquakes in this side, but very little down there. And although the distance from the fault to Mexico City is probably on the order of 200 to 300 kilometers, what it does is it basically, the rock filters all the high-frequency waves. Mexico City gets the sort of the long period waves, and everything swings. And so building anything in Mexico City is difficult. So at the beginning of the 2000s, and actually this had been going on for about 15 years, there was a proposal to build this new metro line called the Golden Line. Just I thought I would point out that initially the budgets were about $1.2 billion. And as you can see on the little image up at the top right, most of these were supposed to be underground lines. Okay? A year later, after the project matured a little bit, here's what we have. Almost everything, as shown up here, all of this part here is elevated. Okay? And the reason for it being elevated is basically speed of construction. Okay? And the speed of construction was tied to this fellow. Marcelo Ebrard, he was the governor of Mexico City, and being governor of Mexico City is like, Mexico City is almost a country unto itself. And so he is currently the Minister of Foreign Affairs for Mexico, and he is one of the two most likely candidates to be president of Mexico next time, after Mr. López Obrador leaves. Okay? And you can see him in this picture under one of the construction sites for the metro line. A couple of other things that I need to point out. Anybody knows what that name is, Carso? I'll come back to that in a little while. But the story is long and complicated, and I'm going to try to keep it relatively simple. There were lots of changes that were driven by political and what I would call economic interests. The major one was that everything in Mexico City, they have a very large metro system. It's been around for almost 50 years. Everything is on rubber wheels. Guess what? They decided to switch to steel wheels. Okay? And they had very little experience with that. The other thing is that because they wanted to hit all of these very populated places, they wanted to go on the roadways, on an elevated roadway. And that resulted in having a lot of very sharp curves on this thing, which is not really good if you're trying to put in a transportation system, because it considerably slows down things. The third thing that's interesting is that Mexico City does not have a code that addresses steel bridges. Okay? They have things and Mexico on the whole does not have a code that addresses bridges. They have it for buildings and so on, but they adopt AASHTO. So this project was supposed to be designed by AASHTO, and so a lot of the things that I'm going to say next relate to checks that one would have done against AASHTO. The choice of steel was also, again, driven because Mr. Ebrard only had about 5 years to finish this project because he cannot be reelected, right? And so he had to complete this in his period, all right? And so building it in concrete was going to take a little longer, and they decided to build it in steel. There's very little experience in Mexico in building steel bridges. There are a few companies that do it and do it very well. The one that was chosen was the best firm that does buildings. And Ted actually knows the guy that run that firm. And so lots of issues came up, and we are able to trace all of them because on the right-hand side is the signatures of all the people that approved the plans. And all the plans are public, and all the calculations are public. So you can actually go and read and check the calculations. So here's sort of the general layout of the project. A single concrete pylon, a concrete cap beam, and 2 steel girders on the top. Okay? And what you see at the top are the precast slabs that were being used for this. And I'm going to come back to those in a minute. So here is a diagram of or a cross-section of the main structural portions, and I'm going to concentrate myself only on the steel and the concrete portions, because this is supposed to be a composite system. And the most interesting thing that I have to tell you to begin with is if you look at the red outlines for the big steel girders, those are to scale. And so if you compare the size of the bottom flange to the size of the top flange, you would immediately hopefully guess that there's something not right on that. The idea was to build these things and then come in with those precast panels that I showed you, right? Put the precast panels there. I don't know if you noticed, there were some holes on those precast panels. I'm going to come back to that. That's where they were going to weld the shear studs through, and then they were going to put a little finishing portion in concrete up here, cast in place to make the whole thing work together. That was the idea. There were lots of design changes because when you go from a rubber wheel to a steel wheel type of train, the ballast and everything else changes quite drastically. And so there were lots of things that naturally kind of got lost in the process. But if you just look at if you just look at this cross-section here, I was talking before about the fact if you take the area of the top flange and the area of the web, right? Hopefully that should be about half, right? You look at this beam, the area of the top flange is generally, and the area of the web is much less than the area down here. So if you look at what we call the plastic neutral axis of this girder, it's actually sitting in the bottom flange. This ain't right. And so if you go through the checks, and again, I'm just flashing these up there because we went through the whole thing, right? There are all some of the checks that you have to do on the geometry of the girder by AASHTO, and there are at least 2 that are way, way off. And again, for those of you who are interested in its stability, right? This is the moment of inertia in the compression flange in the weak direction versus the total. And this is way, way low. The other thing that's interesting is, if you think about it, right, there are going to be large torsional forces on this. This is sitting on a single pylon, right? You got 2 train lines, and the chances that you're going to have a balance load are very small. There's always going to probably be a train on one side or the other. So you need to rely a lot on your cross frames to help the 2 things work together. And it turns out that the cross frames in this case are puny. Yeah, they just won't work. And then there are other interesting things like this strange transitions, and we're going to come back to this because this is where the failure occurred. This little beam here, what is it doing there? And it comes to a point here and is welded. And if you ever think of what is probably the worst stress concentration situation that you can find, is getting that thing it's a crack tip, a built-in crack tip. And there are lots of other things about the DAP ends of the beams there, but we'll skip those. Interestingly enough, if you look at that particular span that I just showed you, everything looked kind of symmetrical and so on and so forth. It turns out that that's not the case because they could only get steel plates in Mexico at a distance of 5 meters. And these are about 30-meter spans, so they needed to weld all of this in the shop. And at least I think most of those were good welds. But if you look at the descriptions here, every section there changes. Okay? There is not one section that's the same. Well, there are some that are the same, but there is also no symmetry whatsoever between the girders. Okay? So it's a really strange design. And the other thing was, of course, that this was going to rely on being a composite system. So once again, that's my little picture, and you can see the holes right there, and you see the elongated holes, right? Those plates were moved over the girders, and they were going to come in and weld 3 studs into each of those. Okay? Now, if you think about construction tolerances, right? Even the smallest of these construction tolerances in terms of the strictness of the girder means that you're not going to hit that hole very well, right? And you're still trying to put those in there. And so the idea was that they were going to come in, do this, and cast some concrete in there, some fresh concrete, and it was all going to act compositely. So Mr. Ebrard was very successful. This thing got open on time, okay? And I'm going to show you, anybody recognize that guy? His name is Carlos Slim. At the time, Carlos Slim was the richest man in the world. He's dropped. He's number 12 now because Elon Musk and people like that have taken over the top of the list. But he was the richest man in the world at the time. And you know what's the most surprising thing? What do you think his profession is? So, if the only thing you take away from this is to tell your classes, right, that you can really get rich at being a civil engineer, right, here it is. He is the owner of the construction company that I mentioned before. Okay? But you can understand here what I'm trying to, and very quickly, because this is a very complicated web of interactions, is giving you some thought about how all the politics and the technical things and everything just kind of got together. And so immediately, within about less than a year and a half from the opening of the new line, it had to be shut down, and shut down for quite a while, because all the rails were cracking. And the rails were cracking because the turns were too sharp, number one, and there had been some problems because when they changed the design from rubber tires to steel tires, they hadn't accounted for the fact that if you go on very tight radiuses, you're going to get very uneven wear of the tracks. And so here are a couple of pictures, and again, I'm going to have to point. So you see on one side, the wheel is bearing. On the other side, not even close. All right? So these are construction tolerance issues. And so this meant that the entire project ended up almost, in terms of the tracks, being rebuilt from scratch. And so almost immediately after it opened, within about 16 months, it was closed for about a year and a half. When this happened, they also noticed something pretty strange. There was one particular overpass or section in which they had large deflections. Okay? And when I say large, they're large. You can see them here. Okay? And there was web lateral buckling and web local yielding and all kinds of things going on in here. And so when they saw this, and it's not, actually what is not clear there is that there's also a fairly large lateral deflection on this whole thing, right? But, you know, this is 39 centimeters on 30 meters, right? So that's less than about L over 80. okay, of deflection. And nobody asked the question at that time, why did that happen? Right? What they did, of course, is they immediately came in and shored it, right? Jacked it up, and then came and built this thing to support the structure. Now, look at this, and I'm going to show you a very similar picture of the fix that they're doing. All right? Next comes a little earthquake, not a little, a fairly major earthquake nearby in Puebla. And there are problems with the concrete stuff. We don't know how well they were inspected. This is the only one that failed, but for those of you who are into reinforced concrete, there is one transverse reinforcement there, right? And where's the next one? Nowhere. So this just basically exploded. Theoretically, there were only 3 of these that got fixed, and they got fixed by covering them with FRP. And so in the end, it looks pretty. It looks just fine. But we don't know how many of these are actually potentially susceptible to the same type of damage. Actually, this is a good picture to look at the bracing and just get a sense that that's not hefty bracing at all. It's not what you would see in a typical bridge in the US at all. And so the last part here is the Olivos station. This is where the failure occurred. This is the entrance into a station. And so remember that little transition area there? Kind of weird. And so last year, about 18 months ago, late in the evening, when a train was going over the entrance to that station, that span collapsed, killed 26 people, 79 injured, just a complete disaster. And so obviously, after the initial response, which was quite chaotic, because you can see there are plenty of rescuers there, but what can you do about a situation where everything is in a stage of perhaps imminent collapse, right? It's difficult to deal with that. But anyway, when people started to talk about this, immediately there were people that got into the social media and said, yeah, but we have been saying that particular location there was a lot of vibrations as the trains went by. And so one of the great things in forensic investigations nowadays is Google and Google Maps. And you can go and find anything in Google. So this is an image that we pulled out of Google from that location several weeks before. And all you have to do is trace a line there and notice that that thing is sagging quite considerably. Okay? And in fact, in the aftermath, there are pictures that they had from the inspection reports, of which there were preciously few, that clearly show that. And it's not only that, but perhaps to me more interesting is that 3-degree lean over on the side. Now, 3 degrees might not seem like a lot to you, but it's a lot if you think about it. Okay? So this structure gave signs that it was about to fail, but we never listened to the signs. Next interesting sort of political item. Who do they hire to investigate this? They hired DNV, Det Norske Veritas. It's a Norwegian company, very well known in the offshore side of things, not in the bridges, anything. Why did they get hired? Because they work with Pemex, right? Petroleum, the Mexican petroleum company has a lot of offshore plants. They knew them. They were hired to do this. And they did a creditable job. They came out with 2 reports and basically came up with some, what I consider reasonable collapse mechanisms. And primarily it was a lateral torsional buckling of the beams. Because when you looked, and these are the 2 beams just sitting on the ground, And what you can see here are all the shear studs. This is where the beam was. When you go and look at shear studs, these were supposed to be equally spaced, nowhere near. In this location, there were supposed to be 3, as everywhere. There are 2. And so when you, again, I'm not going to bother you with the checks, but clearly it failed. It failed strength-wise. Before we even consider fatigue, which is what probably governs here. And so here are a couple of shots of places where they took out the concrete to look at the shear studs. On the left-hand side, like this one, it's just hanging off the edge there. How well can you count on that? On the other side, they're missing. Now, for those of you who are familiar with this in the US, right, these are Nelson studs, and we have this gun that you do a really good weld. These were all hand welds. Here is one of the welds. A cross-section through the weld, and incomplete fusion, lots of porosities and things like that. In fact, they extracted, the Nostra Veritas extracted one of these, and the test, at least theoretically, in the United States, is that we should be able to pull that stud and get to the ASFU, or the full capacity of the stud. Some of these failed at between 15% and 18% of their capacity. So there was not a lot of interaction there. In that key other little transition beam, that's what the plans showed up there. Where are the studs? They're nowhere. And so, Jerry, this is for you. This is the interaction that we have in terms of the capacity of the system versus the degree of composite action. And one of the things we have been talking about in AISC is the fact that if you have a low degree of interaction, then your studs have to bend a lot, and therefore the studs have to be very ductile. And if you get to very low amounts of interaction, then they just break. And so this curve does not continue like that. And this is exactly where we were with this particular thing. Now, these are quick calculations, not necessarily that. Last item to talk about, all kinds of weld details, okay? Details to avoid conditions susceptible to constraint-induced fracture. These are the tables from AASHTO. These are the designs. They matched almost perfectly. They were doing distortion-induced cracking. Again, this is, again, related to the motion, the out-of-plane motion of the structure. Everything failed here. Last thing is, I mentioned that there were 2 technical reports. The last one was due at the beginning of this year, and that was the 3rd technical report. Ms. Claudia Sheinbaum is the new mayor of Mexico City. She is the other contender to be president of Mexico. The previous 2 reports basically looked at the design and the construction, and that was done by the previous guy, Ebrard. She was very happy with those. The 3rd report, which was supposed to, is what the Nostra Veritas called the root report, the root cause report, blames maintenance and lack of inspection. That's on her, or on her underlings. And so they basically just rejected the report. And the situation is in limbo right now insofar as what's going to be the final thing. Mr. Slim has paid, or will pay, for the entire fixing of this thing at no cost to anybody. And he has paid all the victims. Okay? And we are not going to learn very much more about that. And so miles and miles of this are being fixed like that, which I think they're going to see problems in the next 5 years. But that's the quick fix. And so, how am I doing with time?
You have about 5.
Okay, very quickly. So I just wanted to talk about what happens in the US. And is it that different? So see, this is Fern Hollow. This is a bridge in Pittsburgh. Very nice bridge. AISC actually gave it an award back in '71 when it was constructed. It's a K-frame bridge. There are lots and lots of them around the country. No problem with these bridges, except if you don't take good care of them. And so here's just a schematic of the bridge. Very, again, I think a very nice looking bridge. I'm not going to spend much time here. But it was not very well taken care of. Particularly drainage in the deck was a constant problem from the very early inspection reports that you have. So you have here a spout that should be bringing the water away from the steel. That's not the case. You see this little piece here? That's the brace at the bottom of that. Okay? And this bridge was in terrible condition, and these pictures are from back in 2008 to 2012. I haven't even shown some of the more recent ones. And there were parts where the bridge was gone. But the more interesting thing here is, for those of us who delve into stability, is that as this began to corrode, they decided that they were going to come back and fix it by putting cables. Okay? And you notice that there are two X braces there, and the cables go from top to bottom. Now, this is the good side. That was the bad side. This was fixed in 2011 or 12. Okay? And anybody in their right mind would have thought, okay, the cables are a temporary measure while we finish this, or while we do a real repair. No. And so effectively, right, what we went from is something that looked like this, my little frame on the right, on the left, I'm sorry, to the one on the right. Now, I don't know if this is what caused the failure, right? Because obviously, if you're thinking in terms of stability and buckling, very simplistically, you're increasing the length. But the bridge came down, and so there is a little bit of lateral movement there, but I can't quite tell if that's what happened. Actually, very interesting because, NTSB is doing the research, but one of the things that's most interesting for me in terms of forensic engineering is that now we have cameras everywhere, right? So this is the camera on the bus that you just saw. And this is the camera facing forward, and this is the camera facing backwards. And that bus is going down, almost as we speak. But you can sort of tell a little bit, right, that there's a separation there, and this is actually moving a little bit sideways, probably. Okay? So much more investigation is needed on that. I actually think that the failure occurred, and I don't have the time to go into it, because of corrosion in the splices. Okay? And there's a lot of evidence in some of the reports that corrosion was between 50 and 90% through some of those bolts. And nothing had been done. We wanted to get the calculations. And so I was telling one of my colleagues that I no longer work for consultants, I work for newspapers, and I work for free for newspapers, and I talk to newspapers. And so through the Freedom of Information Act, with a journalist at the Pittsburgh Post-Gazette, we tried to get all the reports. And they did, except all the interesting parts are in black. We asked why. And they said, national security. And we said, what? And they said, yeah, somebody could try to blow up that bridge. And we said, that bridge is down. And I thought that was a very powerful logic. It did not get us anything from the city of Pittsburgh. And the other thing is, right, just like in the case of Mexico City, and I'm not going to talk about Minnesota and the I-35W bridge. What happens in the aftermath of something like that? You get it rebuilt as soon as possible so people don't complain. And so that's where they're at. And so I'm going to end my story there with just a couple of things. Going back to sort of my overall thesis, and here is another book, if you're interested, that's The Next Catastrophe, that's from Charles Perrow. He has written a lot on failures from the sociology side over time. And so his point is, going back to this idea that we are concentrating resources and population and so on, he says that the most important thing that we should be doing as engineers is reducing the size of vulnerable targets. We need to sort of separate things. All right? And one last issue is, what are we doing about it from the standpoint of the profession? So when I was president of SEI, we went to England and talked to to our colleagues at the Structural Engineering Institute, and they have what they call the cross system, which is a system in which you can document failures in an anonymous way. Because the problem that we have in the United States is obviously because everything ends up in litigation, and almost every litigation ends up on some sort of settlement, then we never find out the technical details of what actually happened, because everything is sealed. And so this is our answer to that, and that's being pioneered by Glenn Bell, who's past president of SEI and principal at SGH in Boston, which you probably know Glenn quite well. And so that's the end of my story, and thank you for putting up with me.
Thank you for a wonderful presentation. The question that I have is that it seems that there's a lot of red flags all over the place. But is there like a way of just like bringing them up without people just blowing it off, like it's not important?
Yeah. And so, yeah, so here the idea, right, is that even the workers, the construction workers should be the ones that have a voice, a big voice in all of this, because it's their safety that is at stake, right? They are the ones who suffer directly in many ways. And so to me, the idea is that we need to have a much less fragmented industry in which people communicate a lot better, right? Because you can find plenty of failures that are the result of just poor communication, right? And so on. And so, I think that for example, for the Hollow Fern Bridge, right? I've read all the reports, and when I talk, if you go back and try to read some of what I wrote or I talked to the journalists in Pittsburgh, I said I found sort of the smoking gun in a report from 2013, I believe it was, where the inspectors actually said, you know, the cables are still there. We thought that was temporary or something to that effect. And it's the only place where anything like that appears. And it is really strange, right? Because you look at the pictures, you know, and again, these are pictures from inspection reports for many years, and you would say something needed to be done. Somebody had to look at this. And so I think my point there is that, you know, I was sort of being hard on Mexico, but, you know, these things happen everywhere.
Any other questions?
Thanks for a great talk. So I'm not a structural engineer. Are there no requirements to do something about these inspection reports? I wonder why they even bother to inspect if there's never any required follow-up.
So there is required follow-up because, you know, obviously due to the collapses of bridges, particularly the one that the Point Pleasanton Bridge in 1967, right, we have this requirement from the federal government that bridges need to be inspected every 2 years, right? But the question is what happens to those inspection reports. So this is the city of Pittsburgh, and city of Pittsburgh probably has the most bridges in the country. Okay, so you have to be conscious of that. They also probably don't have a lot of bridge inspectors and so on. And so the best thing that we were told is that this report, the last one, was probably sitting in a stack of things in somebody's desk. But the idea is somebody as an engineer that saw this should have stopped and said, we need to do something about this, right? It's obvious, but it gets buried in a lot of paperwork. The other thing is that the way they prioritize replacing or retrofitting bridges is a big issue, because most of them get prioritized in terms of the safety to humans. And so going back to my second project here, it was actually a project with PennDOT and Ted Krauthammer, and we were looking at prioritizing the replacement of bridges in Pennsylvania. And the algorithm that was being used basically placed a very large amount of money on life safety. And so if you were going to prevent, statistically, an accident that was going to kill one person, that was worth like $10 million, right? And so that immediately kind of overshadowed everything else. And so, and apparently here, just to conclude, I mean, it's not like they weren't aware of this, it's just they weren't aware of how urgent it was.
I'll ask a follow-up just because I have the mic. When you say that the engineer should be able to say, hey, we need to do something about this, how does that happen? Is it through the press?
Well, no, I don't know if it's through the press, but ideally, the bridge inspectors are not necessarily engineers. They have been trained to look for things, right? And they know how to look for things, and they actually document things pretty well. So if you look at the reports, I would say are good. Is what happens afterwards. And so, again, these are generally done by private companies, okay? And so, and they will just pass this along, and that's their responsibility. They just, but they might change the inspection company from year to year. So sometimes you see gaps, and you can tell because the reports look different. But then the communication is lost. The continuity is lost. So this is why I'm saying that the industry is so fragmented that we need to be able to communicate these things better. But I've had the situation on my own campus where I was walking, the bridge, yes. And there was a panel that was hanging off the underneath of that bridge that looked crooked. And I immediately called facilities, and I said, I'm staying here until somebody comes and looks at that, right? But not everybody does that.
Well, with that, I'd like to thank you, Roberto, so much for your excellent presentation. And we have a small token of appreciation.
Oh, thank you.
And also for our audience here, I want to remind you of the events this afternoon starting at 4 p.m. over in room 100 Rapson, a seminar in honor of our Professor Emeritus Ted Galambos. So with that, I'd like to give some applause for Professor Leone.